Hi everybody, and welcome back for Unit 6, Lesson 10, which is called the Fundamental Theorem of Calculus. Now you know if it's fundamental, it's going to be not only fun, but also very important. So this is going to be a very important idea for us to master today. The learning target for today is I can apply the fundamental theorem of calculus to find the derivative of a function that is defined as an integral. So the first thing we're going to do today is talk about finding the relationship between derivatives and integrals. So we know now that one of the things we've learned how to do is take the derivative of a function. And another thing we've learned how to do is find the antiderivative and integrate a function. What we're going to do now is both to the same function. We're going to do the integral, and then we're going to do the derivative of that, and then we're going to see what we get at the end and see if there's a relationship between the final answer and what we originally started with. I'll give you a hint. There is a relationship. We're just going to try to figure out what that is. So this really means we're going to do things in two steps. Step number one is going to be we're going to evaluate the integral. Step number two is going to be that we are then going to find the derivative. So step number one, let's do the integral. So I know that at the end of this, I'm going to do the derivative of whatever I get, but I'm just going to work on right now finding the integral. So in order to evaluate this integral, I'm going to start with the antiderivative. So the antiderivative of cosine would just be sine. And I'm going to evaluate that between my lower bound, which is 3x, and my upper bound, which is x squared. Now you might notice that these bounds look a little bit different than what we're used to. Usually our bounds are numbers. In this case, they are functions of x. So we're going to see how that relates to our final answer. Now we're going to plug in the upper bound. So we're going to have sine of x squared plus c. And then we're going to plug in the lower bound. So we're going to have sine of 3x plus c. And then we're going to simplify. So the c's cancel. And we just end up with sine of x squared minus sine of 3x. Now, step number two here is that we want to take the derivative of that. So we want to take the derivative of what we just got as our answer to our integral, which is the derivative of sine of x squared minus sine of 3x. Now, in order to take the derivative here, we're going to need to use chain rule. So we're going to take the derivative of the outside first. So the derivative of sine would just be cosine. Leave the inside alone. Times the derivative of the inside, which is 2x, minus, then we're going to take the derivative of the outside, so cosine of 3x times the derivative of the inside, which is 3. All right. Now let's look and see if there's a relationship between the final answer here and the original problem. Because it's possible that when we need to take the derivative of an integral, we don't have to do all this work. We might be able to skip a bunch of steps because we see that there's a pattern. The first thing I want you to notice is that the original function had a cosine as its function that was the base function of the integral. And you'll notice that in the answer here, there's a cosine function as the base function. Now, the original problem, the upper bound was x squared. And I know when I evaluate an integral, I always do the upper bound first. And you'll notice in the first term here, what's inside of the cosine is the x squared. And then the lower bound was the 3x. Now, I know that when I do an integral, I always do the lower bound second. And you'll notice that the 3x is in the second cosine function. So it looks like my final answer here was just the original function with the upper bound plugged in, and then minus, and then the lower bound plugged in, which is kind of how I do an integral. But the other thing I want you to notice is that there's another piece here. We have these two pieces which were not part of the original, the 2x and the 3. And those pieces are there because they were the derivatives of the bounds. The 2x was the derivative of the x squared. It was not the derivative of cosine. It was just the derivative of the x squared. And the 3 is there because it's the derivative of the 3x. Again, not the derivative of the cosine, just the derivative of the bound that we ended up plugging in. So how could we skip this step? It looks like we had a sine here for a while, and then we had a sine here, and then we took the derivative and we got a cosine. Well, it turns out that whenever you take the derivative of an integral, because an integral uses an antiderivative, and then you're just going to do the derivative again, you're going to end up with the same base function that you originally started with, because you're going to do the antiderivative and then the derivative. So anytime you take the derivative of an integral, whatever function was inside here that you started with, cosine, e, whatever, it's going to be the function you end with. It's going to be the same thing. The only difference is going to be that you're going to end up with the bounds plugged in. So you're going to end up plugging in the upper bound and then minus and the lower bound and doing the chains of the bounds, not the chains of the original function, just the chains of what you plugged in. That rule right here, the idea that a derivative and an integral are almost like inverse operations where they kind of cancel each other out, is what's called the fundamental theorem of calculus. And what this says is, if you do the derivative of an integral, the function you end up with is going to be the same thing as the function you started with because these are inverse operations. You're going to do the antiderivative and then just do the derivative again and get back to where you started. So here's how we write the fundamental theorem of calculus. Here's how we say it. Whenever you do the derivative of an integral, you're going to end up with the exact same function you started with. So it's going to be f of something minus f of something. But you're going to plug in the upper bound and the lower bound as part of the process. And you need to still apply chain rule because you're still taking a derivative. Even though you're skipping the steps where you took the derivative, you're still taking a derivative. So you're going to have to do the derivative of the bound, not of the original function, just the bound that you plugged in, and then the derivative of the bound as the chain for each of those. So you're just going to pop in the top, take the chain. Pop in the bottom, take the chain, whenever you're doing the derivative of an integral. So how does this play out? Scenario number one is that the upper bound only is a function of x. So I'm going to give you some equations, and we're going to find the derivative for the following functions. Now, remember, when you're taking a derivative, the derivative of a number is 0. So that's important to remember here. So when I take this derivative, even though this says do the integral of sine and then take the derivative, we know we're still going to end up with sine at the end. And the reason that happens is because the derivative and the integral are basically inverse operations. So I'm going to end up with sine of something minus sine of something. The first something that I'm going to plug in is the upper bound, which is x. And the derivative of x, the chain, is just 1. Don't forget to do the chain rule. Then I'm going to plug in the lower bound, which is 4. Oh, it should be something squared. X squared. I forgot that there was a squared there. You can see that there's a t here. It's t squared, so you're plugging in its x squared. The second function is going to be 4 squared. And the derivative of 4 would be 0. Now, anytime you multiply by 0, it just becomes 0. So this part of the problem right here just becomes 0, which means your final answer here would just be sine of x squared. And you don't even really have to write the times 1 because it doesn't change anything. So what you end up with here is just sine of, instead of t squared, it's x squared because you plugged in the x into your function. Now I'm going to tell you, normally we skip this step. Whenever your bound is just a number, the derivative, the chain, will always be 0. And so because of that, we normally skip that step. Now let's take a look at the next one, number 2. So if our top bound is a function of x and our bottom is a number, let's see what happens here. So our derivative, our rule for taking the derivative of this integral is Just keep the function that you originally started with, the sine of something squared, and just plug in the bounds. So I'm going to have sine of something squared. And since the bottom is a number here, I'm not going to put the minus something else because the derivative of a number is 0. So I'm only going to be plugging in the top bound. When I plug in the top bound, I get 3x squared plus 7x inside of here. And then I just need to do the chain, which is 6x plus 7, and I'm done. So just drop it in and do the chain. Now, what if, scenario number 2, only the lower bound is a function of x? So what if we have something similar, but only the bottom has an x in it, the top is just a number? Well, just like we said in the other problem, the derivative of a number is 0. And so when I plug in my bounds, I'm going to have dy over dx equals. Normally, I would plug in the top number first and then put a minus, and then the second would be the bottom number. But because this is going to be 0, I'm just going to skip that part, and I'm just going to put a minus because the beginning is like a 0. Like this top is like 0 because the derivative of 7 would just be 0. So I'm going to have minus, and then I'm going to keep my function. So it's sine of something squared. What I'm plugging in this time is the 3x plus 2. And then I need to do the chain, which is times 3. So it would be negative sine of quantity 3x plus 2 squared times 3. Now, if you want to write that in a little bit of a neater way, a lot of the times you're going to see it written like this. Negative 3, we're just moving the 3 to the beginning. Sine of 3x plus 2 squared, like that. What if both the upper and the lower bounds are functions of x? So what do we do if everybody is a function of x? Well, in that scenario, you're just going to do what we kind of did in the first example that we did way back at the beginning. You're going to keep the original function. So it's going to be 1 over 2 plus e to the something. And there's going to be a minus, and it's going to be 1 over 2 plus e to the something. You're going to drop in your top bound first, so it's going to be x squared, and then times the chain, so 2x. And then you're going to drop in your bottom bound second, so it'd be 2x, and then times the chain, which is 2. So it's just keep the original function, drop in the bounds, and do the chain rule. Now, what if we want to find the derivative of an accumulation function? Now, a function that is defined as the integral of another function is called an accumulation function. So in this case, g of x is an accumulation function. Because in order to find values for g of x, you need to find the accumulated area of a different function, which is f of x. So that's why we call that an accumulation function. F of x is not an accumulation function. F of x is just part of the integral. G of x is an accumulation function because it's equal to something that involves the integral of something else. If you want to find the derivative here, we're just going to do this one part of the function at a time. So first we're going to do the derivative of 3x, which would just be 3, plus, now we're going to do the derivative of an integral. So we're going to use the fundamental theorem of calculus. The derivative of this integral would just be f of something. And then I'm not going to do the minus because the bottom is just a number. So I'm only going to be plugging in the top bound. If I plug in the x, I get x here. And then the chain would just be times 1. So I'm not going to write it. So your derivative here, your g prime, would just be 3 plus f of x. Next, for number 6, g of x is equal to the integral of f of t dt. So g prime, we're just going to use the fundamental theorem of calculus, which says when you take the derivative of an integral, you stick with the original function. So I'm going to have f of something, and I'm not going to put the minus because the bottom is just a number, so the derivative would be 0. I'm going to go ahead and plug in the top bound, which is x squared. This time the chain is 2x, so I am going to write it. Last but not least, for problem number 7, I'm going to take the derivative of an integral, and the fundamental theorem says that that just means you have the same function you started with, but you've got to plug in the bounds. So I'm going to drop in the 4x, and then the chain would be times 4. A lot of times you're going to see that written with the 4 at the beginning, 4 times f of 4x. A lot of times you'll see this one written with the 2x at the beginning, 2x times f of x squared. It doesn't really matter. You can write it either way, as long as you know how to find the derivative and you don't forget to use the chain rule. Okay, that is it for today. Thank you guys so much for watching, and I'll see you soon for some practice.